My name is Thomas Fan, and I'm presenting you Skorch, a union of Scikit-learn and PyTorch. How many of you have heard of Scikit-learn? Yeah, all of you, looks like. Scikit-learn provides an interface to Python, it provides a unified interface to define your machine learning algorithms. So in this case, you could define a stochastic gradient descent classifier. If you want to train it, you call fit. If you want to predict from it, predict. Some algorithms allow you to do online training, where you can continue training your algorithm, which you call partial fit. And specifically to scikit-learn, you could change the hyperparameters of your classifier by calling set params, right? Very standard stuff. How many of you have heard of PyTorch? Oh. All right, I could skip through a lot of things. PyTorch, if you want to train a neural net, you could easily write for loops to train a neural net. But normally, you want to do more than that. You want to record metrics. So you write some more code to do that. But back in kindergarten, we learned that we have to split our training data into training and validation sets. So we do that as well. And there's a lot more stuff we have to do. We have to calculate validation losses, do some sort of saving of our model, record other metrics, logging, et cetera, et cetera. So these pieces of code you share between your deep learning experiments, and you'll have to rewrite them over and over again. Skorch provides a way to unify what you do. It's a scikit-learn compatible neural network library that wraps PyTorch. It abstracts away all the code we just saw, so you don't have to think about the training loop or the evaluation loop. And who here is familiar with Keras? Keras, right? Keras, so taking inspiration from Keras. Skorch also uses callbacks to reduce boilerplate code, okay? The big object in Skorch is the neural net object, which is you could import it from the top level module. It takes a module, which is how PyTorch defines a neural net. To train a neural net, you also need a loss function, which you define using that criteria parameter, and it takes in a list of callbacks. Rather than going through the API and just spewing you what the Skorch API is, I thought it'd be fun to go through some example data sets and show you how we could use Skorch to solve these problems. So first, the MNET data set, pretty simple. Next, an ants versus bees classifier, which we will use transfer learning. And lastly, the 2018 Kaggle Data Science Bowl, which is an image segmentation problem. Okay, MNET data set. Everyone knows the MNET data set? 28 by 28, grayscale, labels between 0 and 9. There's 70,000 of them. If you flatten the 28 by 28, you get the 784. Okay, simple. Remember, kindergarten, we have to do our train test split to split our training data into training and test sets. Notice in this case, I manually scaled my data set by dividing by the maximum value. So now our x values are between 0 and 1. For this example, we're going to create a simple module, a feed-forward neural net. It takes in an input of size 784, goes through some nonlinear functions, spits out an array of 98, goes through another function, and at the end, it spits out a vector of size 10. For those who don't know, to define this module, you have to subclass the module class from PyTorch. Remember to call super init in your init under init function and define a forward method. Then you can write this module, this diagram in code. Notice that my init under init method has a dropout parameter. Okay, it's equal to 0.5. I'll come back to this in a moment. Next, to train a neural net, we need a loss function to optimize. One common way to define a loss function is as follows. The neural net will output a vector of size 10, which could be any real number. So in this case, in this example, this vector. If you want the probability, take the softmax. And if you want a loss function, you take the negative log of it. In PyTorch, there's something simple, the cross-entropy loss. Okay. Now, so you have the module and the criteria. So you place that into the neural net object in Skorch and the criteria. And there's 3 more parameters you should set. The max epoch is how many times you want to run through your training set. And the learning rate, which is a hyperparameter to the algorithm to optimize the loss function. Lastly, you need a device. And if you want to run it on a GPU, you set the device parameter to CUDA. If you want to run it on CPU, you could comment it out and run on CPU. So the moment of truth. Next, we could just call fit on this neural net and object, and it will fit the neural net like so. Notice that it outputs training loss, validation loss, and the duration of each epoch. We didn't really split the training set into a validation set. Skorch does it by default, splitting our training set, in this case xtrain_train, into 80% training and 20% validation. Remember that Scikit-learn has a set params method. And in this case, if we want to continue training this neural net, let's say this is not good enough, for only 5 epochs, we could do that. We could call set params with the max epoch equal to 5 and call partial fit this time. Partial fit continues training the neural net. And remember before we started at epoch 10, now we start at epoch 11 and then epoch 15. After training, Skorch has a special object called history, which stores all the data we just saw before. The length of the history is how many epochs we trained the neural net. It could also do indexing. So in this case, -1 means that we want the last item of the validation loss column. Right? That works. We also do Python slicing, which is as follows. If you want the last 2 values, you use -2, normal slicing. Simple. There's other metrics you could use. In this case, let's say you want to do accuracy score. For accuracy score, we have to define a Scikit-learn scorer. Who's familiar with the score interface in Scikit-learn? Kind of. All right. It's very easy to define a Scikit-learn score interface. You define your own custom score metric. In this case, it takes the true value, the predicted value, combine them to form the accuracy score. Afterwards, if you want to create the scorer objects, Scikit-learn provides a make scorer function that gives you the scorer. So simple. Now, Skorch has a callback, our first callback, called the epoch scoring callback. It takes in the score we just created. You have to name it so it knows what to put on the log. And importantly, you have to set lower is better to false, because at higher accuracy score is better. Next, we just stick it into our neural net, put it in the list of callbacks, and call fit. Notice now we have a new column called validation accuracy, valAcc, as we named it before. And this is the accuracy of the neural net model over the epochs. If you want to call predict now, you could call predict just like Scikit-learn, and it works. And if you want the accuracy, you could call accuracy. Since Skorch supports the Scikit-learn API, you could use it with all the other Scikit-learn APIs, such as pipelines. Right? So with pipelines, we don't have to do that scaling we did in one of the first few slides. We could just use Scikit-learn's min-max scaler, stick it into a pipeline, and call fit, and this will do all the processing for you, and it just works as well. Next, since Skorch also supports the set params and get params paradigm in Scikit-learn, you could also grid search over it. Grid searching by calling grid search CV. You can also do random search CV as well. And if you're who's familiar with this API, the grid search, you could do hyperparam searching. You use the double underscore to denote which parameter you want to change. Remember, our module had a dropout parameter. In this case, I want to vary my dropout parameter by 0.2, 0.5, and 0.8. And we could do cross-validation with the grid search API, and everything just works as well. Okay, so the MNET dataset is a very simple dataset. It fits into memory. Usually when you do deep learning, everything doesn't fit into memory, right? So as an example, I'm going to use an images to train a neural net classifier to distinguish between these beautiful images of ants, if you find ants beautiful, and then lovely images of bees. Okay? To get the data out of this data set, if you look, when you download the data, you get the images into these folders where the training and validation set is already split out for you. So Torch Vision comes with this very special object that's called an image folder, which you could define as follows. We'll come back to what these train transformations do in a second. I want to focus on the image folder for now. The image folder is a subset of Torch's dataset object. It acts just like a list. You call length on it, and it gives you the length. You could index it, and it spews out a tuple where the first value is the image, and the next value is the target. And in this case, the target is 0. And 0, in this case, represents ants, and 1 represents bees. Recall that I had a transformation thing at the end of my image folder definition. Let's look at that now. So in this case, these are transformations on the images in the train folder. It's very typical when you do neural networks, when you train a neural network, to augment your data. You do some random flips, you change the colors a little bit, and one way to do it is to use Torch Vision's transformations to help you do it. The most important thing here is the normalization. We're going to normalize our data to this mean and the bottom standard deviation. The reason we do that is to use a pre-trained neural net in this case, which was trained on ImageNet. So to use this pre-trained neural net, we have to normalize our data to the mean and standard deviation of ImageNet. For this example, we're going to train it on a ResNet model, which is as follows. You take in a 3 by 224. 3 represents the colors. You're going to push it through many layers of functions, and at the end, it will spit out a vector of size 2, where 0 represents ants and 1 represents bees. To do this in PyTorch, it's very simple. You use the Torch Vision's ResNet 18, make sure your pre-train is true, and at the end, you see how I replace the last layer with a linear model, outputting a vector size 2. Notice that I named the last layer model.fc. This will be important in the next slide. Because when you do use a pre-trained neural network, it's kind of standard, to freeze the layers as well. So in Skorch, we have a callback called freezer. And in this case, I want to freeze the layers where the name does not start with model.fc. So this is everything over here in blue. The red layer is everything you want to train. Okay? It's also standard to vary the learning rate as you train your neural net. In this case, we could use a callback called the learning rate scheduler, the LR scheduler. In this case, the learning rate starts at 0.1, and it drops to 10% of its initial value every 7 steps. What more could we do in Skorch? We could do checkpoints. We're going to use the same accuracy score as we had before, using valid accuracy. This is the same epoch scoring we had in the first example, but now we have a new callback called checkpoint, which takes in this case, 2 parameters. 1, to specify the directory we want to save the checkpoint files in, and what to monitor. in this case, you see that the name of our epoch scoring is val. In this case, we want to save the checkpoint when the validation accuracy is at its best. Okay? Now, with all these callbacks, we just stick them all into a list of the callbacks. And this is different. Since we already have a validation set predefined in our folder structure, we have to use this helper method to tell the neural net to not split the training set by itself, but use our own validation data set in this case. So this does it for you. You could call fit, and it just works. Notice that there's now another column called CP. CP with a plus over here means that this accuracy score is the best value at epoch 8. And when it will save the state of the model at that point. If you want to look at the folders, what did the checkpoint save? You can look at the directory. Remember we called the directory exp_01, so forth. It saves 3 files. The history, which is a JSON, which is very nice, where you could look at the logs that we had seen before, and an optimizer, the parameters of the optimizer, and the parameters of your model. So params.pt is the parameters of your neural network. At this point in time, if you were in a Jupyter notebook, your model would be at epoch 10, which is not the best model. The best model is at epoch 8. To load those parameters, there's a function called load params. And you can pass in the checkpoint, which saves the model epoch 8, and this called predict on it. And it will run through your neural net for this data, for the data in this data set. If this was not in a notebook, let's say a script, there's an important point to make. Let's say this is another script. You train your neural network in a training script. You have another script to do predictions. So this checkpoint is exactly the same as we saw before. This net object is exactly the same as we had before. But in this case, we have to initialize the net. Because when we define the neural net in the init method, these objects, the pre-trained model, is not initialized yet. You have to initialize it first, and then you could load the parameters of your checkpoint into the model. And now you could predict as before. All right. Oh my God. What's more? Let's say you want to Dockerize this thing, right? You want to use it with NumPy. The first thing you have to make sure is your NumPy is of the correct shape. In this case, 3 is the colors. In this case, I want to run the neural net through one image, represent the 1 in the beginning. And you could predict on it, and it would spit out a number, an array of size 2. And if you want to know the probability, you call softmax. Okay? That's simple. Next, remember the last item I want to talk about is the data science bowl. The data science bowl was a Kaggle competition this year, which had to do with images of cells. And we want to the data set consists of 3 types of images. One where it's kind of purple, one where it's black, and one where it's whitish. And the data set consists of the corresponding mass along with it. You see that the whiteness corresponds to the nuclei of your data set. In this case, I had to define my own dataset object, which I call cells dataset. Okay? The cells dataset is also a list-like object where you could index it like a list, and it would spit out a tuple of images and mass. So the first item is the image itself. The second item is the mass. For the model we want to train in this example, we want to train a UNet class neural network. In this case, it takes an image of size 3 times 288, runs it through a nonlinear layers, and it will spit out an image of 1 by 288. Okay. in this case, we want to use transfer learning as well. So it'd be good to freeze some layers as well. So we could use Skorch's callback API with the freezer as well, and give it the name of these 4 layers, which I called CONV number. So in this case, freezer also supports a glob. In this case, you see it's globbed with COV. So this will freeze everything that begins with COV. When using a UNet classifier, it turns out it's very bad at the borders of your images. So in this case, it's very bad at doing classification on these edges, on the edges. So one way to work around this is to use a reflection on the edges of your image. Okay, so you see how this, at the end, there's this reflections of the inner image. So you expand your image as a whole. Next, the images are not all 288 by 288. So another way to deal with this is, one way to do this is to use a patch data set, where you draw different patches of your data to feed into your neural net. To do this in Python, I created 2 objects. These dataset objects do exactly what I just did before. One common metric to use when you do image segmentation is the IOU metric, where it's the area of the overlap over the area of the union, where if your prediction and your true values overlap exactly, then this value is 1. If they don't overlap, then it's 0. Right? So you want them to have a good overlap over the union. To define this metric in Python, you could approximate it. I won't go into the details of the approximation. It returns the metric. In this case, I want to call make score to create a scoring object. Now, like we had before, we could define an epoch scoring object with the scorer, give it a name, in this case val underscore IOU, and set lower is better is false. Also, we have a checkpoint. In this case, you have another directory name. This is important because the experiment we did before, the experiment before is in another folder. This saves the state of your model in another directory. And in this case, we don't want to monitor, we want to monitor the validation IOU of this scoring. So validate IOU, and you want the best of it. Now, remember that we don't want to count the padding of your image. And so we need a custom criteria for this example that knows about the padding we just did. So we want to ignore the loss at the edges. Okay? So we have a new validation loss that I defined, and it has a parameter called padding. And if we want to adjust this parameter in our neural net object, we could pass in the parameter with the double underscore notation to set this padding parameter to 16, as shown here. And also my UNet object, I just call UNet, the UNet that we had before. How many of you have heard of FastAI? Okay, FastAI, I didn't expect that. FastAI thought of this neat little learning rate scheduler where you start from a low learning rate and jump to a really high one and go back down to a low one. This is called the one cycle policy. And you could also implement this in Skorch as well, using a cyclic learning rate. Yeah, and you have hyperparameters such as the base learning rate and the max learning rate to set where you want the learning rate to be. So in summary, you have this huge neural net object. You give it the callbacks, same as before. You could define a batch size. You could tell it how many epochs you want to go over. You give it callbacks, and you give it the predefined split because we have a validation set we want to focus on. I've been ignoring slight technical-ish details about defining this thing. There's a little bit more parameters to set because internally Skorch uses the data loader object in PyTorch, which consists of these two parameters and more, the pin memory and the num workers. And I like to set these values as such, where this iterated train is the data loader object for the training set, and I like to set the shuffle to true. And this is the more important part. I want to set the num workers to 4, which means we spawn 4 processes to process our images when we do image augmentation, because we want to feed our GPUs constantly and keep them at 100%. Lastly, pin memory is a minor optimization where we don't have to keep on allocating memory on the GPU every time we feed data into the GPU. We do exactly the same for validation. And now we could call fit. And in fit, you get what we expected before. Now we have a column called valid_IOU. And you see that the checkpointed the module at epoch 17, right, with the plus sign. Just like before, we could load the parameters using the load params with the best checkpoints. We could call predict to get a prediction. And these predictions are values that are any view values. So if you want to get a probability, in this case, since it's binary, you could use the sigmoid function. And it would spit out, it would map any real number to any number to a number between 0 and 1. So what does the results look like in this case? It looks like this, where the first column is the true values of the mass. The third column is the images, and in the middle, the start of the show, is the predictions. In this case, you could see how well our neural net does, and this is interesting to me because when I was creating this tutorial, I didn't think this would happen because there are 3 different images, and this handles it very well. So it goes to show the power of deep learning in the image sector. So in closing, PyTorch is a scikit-learn compatible neural net library. We went through fit, partial fit, predict, set params, and because it has set params, you could do the grid search and random search CVs. Random searching in using scikit-learn's random search and grid search to search for hyperparameters for your module. Also, since it supports the fit, you could use pipelines as well, as we saw in the first example. It extracts away the training loop. Notice that how when we call fit, we didn't have to worry about all the little details we had in the first 3 slides. We just call fit, and it just works. Next, we have callbacks. We want to epoch scoring, freezer, checkpoint, LR scheduler. There's a few more that I didn't go over. You could even create your own by going through the documentation. And documentation. The documentation is at this link. There are tutorials that were created that runs on Google Colab. So you could run through the examples in Skorch and play around with the code base. On the issue board, we welcome issues. I'm there pretty much to answer questions if you have any questions with Skorch. And these slides I generated, and the data, the module, or the code I use, or the images are at this GitHub link. So you could reproduce everything I had in these slides if you clone this GitHub and follow the instructions to download the data. Yep, 30 minutes. Yep. Thank you for listening, and that's my talk. Okay.
Are there any questions?
Oh, that's the appendix. I had a lot more slides, and I want to fit it into 35 minutes. Not 30. Yeah, okay.
Hello. Can you do a little compare and contrast with Fast AI and what might make sense to use one or the other?
Fast AI, I wanted to use Fast AI for a while, but if you look at Fast AI's code base, they like to use they abbreviate a lot of things, so it takes a little time to understand how the code works in the Fast AI library. But this is better now because of the Fast AI 1.0. So I think it's good to use both frameworks in this case. Where FastAI gives you the results right away, while Skorch, you have to know a little more details about training a neural net. And if that's the difference, basically, between those two.
In the slide that you had the convolution steps, I think you had L1, L2, L3, and then you had convolution, 1, 2, 3. I have 2 questions. What do you know what algorithms are in those steps, number 1? And number 2 relates to the gentleman's question back here. If you have 2 different paradigms that you're going to use, where are the bottlenecks in each, and why would you use one versus the other, or anything else, depending on the bottlenecks of those particular applications? So first, what are the algorithms in?
There are, have you heard of convolutions?
Oh, yes.
Yeah, so there are convolutions, batch normalizations, and RELU, for the values. LELU, the values.
Okay.
So it's just, that's just it. Those are the 3 building blocks of those convolutions. I think I had the.
Do you know which convolutions in particular?
It's 3. They're all. This is where it's flexible. You could use whatever you want almost in these convolutions, but as long as I typically use 3x3s and 1x1s, like stacked together. But if you read up on it, people have expanded this unit to include whatever they want in these circled blue layers, depending on the problem.
And where are the hotspots?
The hotspots in this. To train a UNet well.
Let me rephrase.
Yeah.
What algorithms do you observe dominating the computation of the entire thing?
It's when you define the neural net, you go through the standard stochastic gradient descent over this nonlinear manifold, and you're trying to find the lowest loss function. In my case, it was the binary loss. What stops this thing from working well? One of the issues, like I said, was the reflection type thing. But what's specifically in this thing, I haven't.
We can talk later.
Yeah, I haven't found a real good one. It answers it answers this math problem really well. But there are some questions where it doesn't work very well. So it works really well for binary maths specifically. So yeah.
Question. What are like the biggest kind of features that will be added on to Skorch?
Oh.
Yeah, I'm just curious. This is pretty awesome.
So at the end of the slides where I just skipped because there's new features such as here, this feature I didn't talk about, which is a train end checkpoint, which will save the neural net at the end of training so that you could do continual training in scripts. So it automatically loads your checkpoint every time you rerun the script. So let's say the first run you run from 1 to 10, you run the script again, it goes from 11 to 20, and so forth and so on. One thing I want to implement now is a Control-C type object where when it exits, it just saves the model for you. So you could save your work if your computer goes down, for instance. So that's something I'm pushing for.
Do you support the 3D convolutions? Like, I know Torch supports
Yeah.
those. Have you extended it to whatever Torch supports?
Whatever Torch supports, that supports as well, because those convolutions are in the module thing. So however you want to define your module in PyTorch, you could define it here as well.
And one other question. I know you unfroze the fully connected layer by calling like a string. Can you unfreeze like indexes of layers? Or?
You know how a module uses name parameters to. So the layers are named, they have a name. If you unfreeze, there's also a corresponding unfreezer callback that unfreezes things however you want. You could even unfreeze and freeze things depending on epoch. So there's a lot of things you could do with the API that I didn't go through. So you could freeze and unfreeze things at will.
Does this work with the PyTorch 1.0 preview that's the latest version of?
It should, because we have to put that version into the CI and continuous delivery and whatnot to make sure it works. But we haven't done that just yet. We will get on that. No.
Hi there. I'm kind of a newbie to the whole AI ML thing, and I'm definitely not a statistician. We're coming from like a governmental space, and I wanted to know, maybe this question is for you, but just also to the general audience. If we're looking to do some kind of object detection, so I'm with the Department of Transportation, and we're interested in knowing where we have high volumes of trucks versus cars. And if we're just getting started out in that kind of sphere, we're familiar with Python in a basic way, but is this a good tool set to sort of pick up first thing, or is there another one that you or maybe the audience could recommend to start off?
Do you need it? How fast do you need the image, the object segmentation? That's
I think
the video. Like, do you do video?
Yes, so we will have kind of I think medium grade resolution video streams coming in from traffic cameras, and my director says I want to know how many trucks have passed by this one intersection every 15 minutes. Something basic like that, but I think if we start giving him something, the appetite will grow.
So you could use this framework with video, with even text. Video is just a series of images. So if you need it in real time, if you need object segmentation in real time, the first thing I would do would be to use traditional, because you're just counting trucks. So you could use OpenCV and just use traditional counting methods to do it. But one of the first neural nets I would want to use would be called the YOLO neural network, which does object segmentation really quickly and into the bounded boxes. And it works really well with video. Right? So if you need it real time, I would just go straight to this algorithm called YOLO v3. You could Google that, and you could use it with Skorch as well.
Okay, so barrier of entry is not too bad.
Yeah.
Okay, thanks.
I think we're
Over time.
out of time. Another round of applause for our speaker.